Hi, I'm Sala, and in this video we are going to simulate several cases of the n-body problem subject to gravitational interaction. For instance, in here we are already simulating a 4-body problem in which, well, the final status of the orbits is sort of difficult to predict. They are sort of chaotic. More on that in a minute. In another video of this collection, we discussed the details of the code carrying out the simulation. We loaded some initial positions and speed in the mass vector, and then we called a simulator which needed a function handle to compute the derivatives of the state vector, and there were 4 state variables per body: position, velocity in x, y coordinates, and the state equation said that the derivatives of the positions were velocities and the derivatives of velocities were accelerations, computed with a gravity acceleration formula in which I computed the vector of position difference between every pair of bodies and the distance, the norm of such a vector. I computed the gravity force with Newton's formula. This was the unit vector in the direction from body I to body J, and this was the attraction force in one body. This was the attraction force in the opposite body, and this loop accumulated all the attraction forces and divided by mass to obtain the acceleration. So with that code, we could simulate these kind of movements. And in here, for instance, we can have this 3-body problem to simulate. Here we have the 3 bodies from these initial positions, and well, initial velocities cannot be seen on screen, of course. And here we have the achieved orbits. They suffer large accelerations when passing very close to another of the bodies, of course. But well, in principle, 3 or more bodies, the final configuration and shape of these orbits is kind of unpredictable, chaotic, in the sense that a very small change in the initial condition of a multi-body gravity simulation can lead to very different shapes and final states in the simulation. And also it's kind of difficult to simulate with accuracy if the planets pass very near each other, because accelerations would tend to infinity if distance is close to 0. But okay, let us concentrate in simulating famous 1-body and 2-body setups. We'll start with the 2-body setup, like Sun and Earth, in which one of the bodies is almost 200 times heavier than the other one. So basically the light body will orbit around the heavy one. We'll put here some initial positions, and well, we can put any arbitrary initial velocity, but in this case I will put velocities like this so that the barycenter doesn't move, in the sense that momentum, sum of mass times velocity, is conserved. And if I set the light body initial speed to -10 0, then putting this velocity initial condition for the heavy body will make that the momentum vector m1 times this stuff plus m2 times this stuff, this was a plus sign, so that this momentum will be 0, and hence the barycenter, center of gravity, let's say, of the system of 2 bodies the weighted sum of the positions, well, that will be the momentum vector, and it will be 0 forever. So with this configuration, if I carry out the simulation, we can see the elliptical orbit of the small lighter body around the big one, which it is almost immobile. And momentum is conserved. The center of mass does not move. If I now put some velocities so that net momentum is non-zero, then I will get the elliptic orbits plus an overall translation of the center of mass, let's say, of this system. So the ellipses get converted into, let's say, springs or screws. This is the simulation. Of course, if I traveled with a drone with a zenithal camera at the same speed as the center of gravity, then I would film the previous simulation. So, sort of, it's a matter of the system of reference I choose. Well, this is the, let's say, one body problem in which one of the objects is immobile, or almost. If we now put two bodies of similar masses and I set up the initial velocity so the barycenter is fixed, we can simulate this new two-body problem, and we'll see that the trajectories describe an ellipse in both of the bodies. The lighter body makes a larger ellipse, but we have kind of two linked ellipses intersecting, at least in planar movement. Here we have them. If we go back to the case in which one of the body is much heavier than the other one, we can think on the heavy body being fixed, and we can compute the escape velocity of the light body with the fact that the potential gravitational energy is this thing, and at any distance energy is conserved. So the kinetic energy, if we think on the light body and disregard the motion of the heavy body, this is why this simplification is called the one body problem. If we are at a distance, let's say RA in configuration A and RB in configuration B, energy is conserved. So potential plus kinetic must verify this. Then if configuration B, we make it tend to infinity, then we get 0 of potential energy when we go to infinitely far away of the heavy body. And in here we will have a terminal kinetic energy, which I will call terminal velocity. It will be the velocity the light body will have when it has escaped the gravitational attraction of the heavy body. When it is very, very, very far away, theoretically at infinite distance, then this will be equal to this thing. When we are at a distance of configuration A, so we have this total energy, and then if we equate this total energy to 0, then the velocity at position A that makes this equal to 0 is called the escape velocity at distance A. It is called the escape velocity because it will have enough total energy to go far, far, far away, but when it has escaped the gravitational pull of the heavy planet, its terminal velocity will be 0. And if its initial speed at position A is strictly larger than the escape velocity, then when it is very, very far away, it will have a finite non-zero velocity to keep on exploring the universe. So this is the concept of escape velocity, and of course from this formula we get that the escape velocity is a square root of 2 potential energy divided by m2, which is equal to, well, this potential energy is in absolute value, in positive. We go to the other side to solve for escape velocity, and then, well, this is the escape velocity when total mechanical energy is 0, let's say, and if total mechanical energy is more than 0, then we will have a terminal velocity. So in our simulation, from an initial position like this is the distance, this is the potential energy, and this is the escape velocity, which is 17.16 units. And for instance, the terminal velocity, which is the terminal kinetic energy, because potential will be 0, it's the total mechanical energy that is conserved. Well, that terminal velocity ends up being 1.2 meters per second, so as 17.2 is larger than the escape velocity, we have terminal velocity non-zero, and if we are close to the escape velocity, terminal velocity tends to 0. And of course, if total mechanical energy is lower than 0, then we cannot go to infinity, because this total energy at infinity cannot be negative. So we will have a finite orbit, and the planet will come back and orbit, the distance to the heavy object will always be finite. Then, if we simulate almost escape velocity, but not there, then from this starting position, it will go far away to sort of 90 horizontal, 70 vertical units, but it will exhibit an ellipsoidal orbit. Here we have it coming back, and the Kepler law, let's say, when it is far away, it's slow, the law of areas, and when it is close to the sun, let's say, then the velocity is fast. So here we have this kind of orbit. And this terminal velocity ends up being an imaginary number, so we cannot go to infinity. But if we put an initial velocity above the escape velocity, then starting at the same positions, it will escape. So now the scale is very different, because it was 90 units away in the previous simulation, and now it goes to infinity. So I will stop the simulation, let's say, when it is 1000 or more away, because it will take, infinite time to reach the simulation. But okay, it just goes away. It has escape velocity. So we finish here. In this video we have simulated several examples of the n-body system subject to gravitational interactions, and well, the most famous ones are the one very heavy body and the light body exhibiting an elliptical orbit if velocity is slower than the escape velocity, or just going to infinity if velocity is equal to or larger than the escape velocity. And we also had simulations where the barycenter moved, other that the barycenter did not move, linked ellipses in two bodies of similar mass, etc. So we conclude here. Thanks for your attention.